Okay, our next speaker is Raul Santos from Phasecraft. This is a contributed talk on efficient and practical formulas for time dynamics. Thanks.
Thank you. Is this working? Can you hear me in the back? Thanks. Right, so yeah, thanks for the invitation, for the opportunity to talk here today. I want to present this result that is just recently in the archive with, on efficient and practical formulas for time dynamics. Of course, I just first want to give a shout out to my collaborators, Gianluca Bose, Filippo Gambetta, which is in the audience somewhere, Andrew, which I think will be here around, Ashley Montanaro, and Charles Derby. So first of all, talk a bit about the outline. So the idea first, I will present a bit of the landscape of time dynamics algorithm. Something has been discussed a bit so far here. We kind of know what's the best that we can do in general, right, in time dynamic simulation, but then that raises the question of what is else to do there, right? So the main point and the main context, the main takeaway from this talk is that we actually really want to solve particular problems in chemistry, in physics. I'm a physicist by training, so you want to solve particular problems. You know your Hamiltonian. You know maybe what the initial state. So you have some initial information. You can use that to actually create better algorithms. In that vein, I will just discuss this drift algorithm, a bit of a playful name on an algorithm that can achieve this in a particular scenario. Present some theory bounds, some results like actually show asymptotics that this actually works, and also back up that with numerics, some particular examples to conclude. So for starters, the landscape of TDS algorithms, maybe here are more experts than me. The idea is that we have different types of algorithms. We know what we can do essentially. You cannot simulate in general a system with a gate complexity smaller than the time that you want to simulate. So there are two. I want to focus here in two parameters. One is the time, the evolution time, which here is t, and the error that you want to achieve, which is epsilon. So there are different methods, different algorithms. We know they're scaling in general. So here just a sample of them. It's like product formulas, but we have this heard from them a lot before. There's the quantum Go algorithm, or like linear combination of unitaries, which kind of inherits this nice scaling just because the Taylor expansion is kind of a great approximation of the exponential. Or we have quantum signal processing, which in some sense it's kind of achieving the best that we can have in general. Okay, so then the natural question is, okay, why? Here's the answer. Let's go back and go home. But the point is that no, we can do better in particular scenarios. So to illustrate that, I think let's look first at an example. So this is a very nice paper in PNAS, where the authors look at a particular example of like the Heisenberg model in 1D with random fields, and they actually instantiate different algorithms, right? So on the left, we have so the field circles are like empirical, theoretical bounds on like the, let's say, CNOT gate complexity. So you want to simulate this system with some error. Let's say, I think that here's 10 to the minus 3 for a time that scales with the system size. And you want to just see, okay, what's the error that what's the error of my algorithm as the system size increases? And what's the, sorry, for a given error, what's the count of CNOTs that I have to implement in my circuit in order to achieve that error? And here we see something particular example. So I want just to focus, that you can focus a bit on the red dots. So the red dots on the top, the field one, are like product formulas. But this is the scaling that comes from the actual errors that you can prove, right? So they are based on commutator scaling and so on. But the empty red dots is actually what you get once you implement these formulas and you look at the difference in operator norm between the actual evolution and the numerical evolution. So they can do this up to like 20 sites, and then they extrapolate. But the main striking thing here is that this big gap, okay? The two things scale with time. Remember, size and time, here in this case, they are tied together. So they scale linearly in this case, but there's a big gap, so the constants matter, right? And although we have better, in particular, the error is, the theoretical error, the theoretical complexity is lower for, let's say, something like here TS is the Taylor series, so like linear combination of unitaries, or like quantum signal processing. In practice, it seems that product formulas actually are outperforming all of those. So, okay, so what's going on? One intuition could be just what Difang said before. Essentially, product formulas have like nice commutator scaling. So in many applications, when you have look at a Hamiltonian that's coming from some physical realization, you have some locality structure, and then if you can exploit that locality structure, then you probably are better off in terms of like your algorithm. So okay, this kind of motivates us to look again into like product formulas, and the context here is that we eventually want to implement this like in computers that are out there. So we have IBM, we have Google, we have other platforms that you can actually try to test these things. You can implement some type of circuits that are not very deep, but you don't want to spend too much resources in like complicated select operations and whatnot, that are needed for like these higher like very efficient algorithms that in the asymptotic limit can outperform product formulas in theory. So here I will just concentrate what can we do with just product formulas? So and the context that I want to concentrate is the context of like a Hamiltonian with two different energy scales. So here it's called, we have H, and it's composed of H0 and H1, and to parameterize the small scale, I will call alpha that small scale, and assume that H1 and H0 have like the same norm. So as we have seen, like I think many times now, a first order total formula, the error scales like the commutator of H0 and H1. And of course, because it has one contribution from H0 and one contribution from H1, then you have that scales linearly with alpha. So a natural question is, okay, can we do better? So here we go again, and we go to the interaction picture. So this is, the intuition is that if you have some Hamiltonian here at H0, and it's a bit of perturbed by H1, maybe you are better off going to the interaction picture, something that has been known like from the beginning of the century in physics. Then maybe you go to the basis where H0 is essentially the one that is implemented exactly, and then you kind of perturb a bit from there. So here's a realization of that. They just going to the interaction picture. So you can think of this as the nice trick. You just trotterize your total evolution, take the limit to n to infinity, and insert identities in between, such that you kind of recover the time order product. And then with this new viewpoint, you can say, okay, let's look at what's the error of an approximation of this unitary, like the error in operator norm, between an approximation of this unitary and our desired unitary. And if we just look at these unitaries in the interaction picture, then we can just forget about H0, because the operator norm is invariant under unitaries and under unitary transformations. So we just have to be able to approximate this time ordered operator. So let's assume, for example, that this time ordered operator, which is controlled by H1, can be split into two parts, like doing a trotterized version of the time independent case, where here I call it H1A and H1B, these two parts of H0. And then if that's possible, then we can get an scaling that actually so an error scaling that actually goes like alpha squared, which would be good if alpha is smaller than 1. So that's kind of the intuition here. We are essentially moving from the time-independent case to the time-dependent case through going to the interaction picture. And in the interaction picture, we kind of bound things better by essentially not caring about the large part, which is H0. But, and you can see essentially the comparison here is just the scaling with alpha, which will be the focus of my talk. How do we make a better scaling with alpha here? But okay, this is nice, very nice kind of mathematical manipulations, but it begs the question, okay, what I'm gaining here, because I'm just making my problem more complicated, And I said that the context is just really to apply this in a particular setting, like going and use it on a quantum computer. So here I just now have to apply 2 time order operators, look what I'm doing, right? So the point is that in this case, when this time dependence came about by going to the interaction picture, you can go back using the interaction picture in reverse. And then that gives you actually, in this scenario, like our approximation becomes of this form, which is just a product of normal exponentials. Okay, all of those are very simple ideas, but the point is kind of a bit deep. Here, if you look, you stare at this formula for a second, you see that essentially is just a product formula, but where you choose your terms in your decomposition of the Trotter formula differently that you will choose it normally. So if you have H1 and H0, remember that the Hamiltonian was H0 plus alpha H1. We could say, okay, you choose H0, and then you choose H1, and then you do that multiple times. Here the idea is that instead of doing that, you choose a bit of H1 together with H0, then in forward in time, then the middle term is like choosing H0 backwards in time, and then you choose the remainder of the Hamiltonian. So that's it, very simple. And the point is that this new decomposition, we just proved before, you didn't know this, but we just proved that this decomposition has an error that actually goes like alpha squared instead of alpha. So this is what essentially can be generalized to having many different summands, and that's what we call the thrift algorithm, which is like a very playful name of this Trotter heuristic resource improved formulas for time dynamics. The heuristic part comes in that there's a hidden assumption here, which is you have to be able to do this H0 plus alpha H1 gamma with an error smaller than the target error that you want. So if that one you cannot do it, and then you have to split it up again, then you will lose all this nice scaling with alpha. But there are cases where you can do that. So I will show some numerical results that back that up. Any questions so far? 5 minutes? Okay. Given that this thing is essentially a new way of looking at just normal product formulas, we can use all the literature that exists on product formulas to improve on this. For example, go to higher orders. Something that's interesting is, okay, we can use it, and we also show that you can go to higher orders and get a better scaling with time, like a normal product formula, but the scaling with alpha remains alpha squared, which is interesting. And the intuition is that essentially, once you go to this higher order formulas, you have like more and more nested commutators, and in one of those, you have to pick up one of H0. So it will have to have, you can improve in time, but you cannot improve in alpha. So the main point is that, okay, we also prove that if you just look at formulas where you just take terms of the Hamiltonian, you cannot improve, you cannot get a better scaling with alpha than alpha squared. So how do we go beyond? Like if alpha is very small, maybe there's a way of getting to arbitrarily good scaling with alpha. And here we touch with this nice Magnus expansion that they also mentioned before. So there's the idea that you can actually approximate the time-ordered evolution by using this Magnus expansion in terms of nested commutators that are given in terms of the Hamiltonian. So the point here is that you define some truncation level, you compute these omegas, which are like the components of the Magnus expansion, and then once you do that up to some level k, then you actually get an error that goes like t times alpha to the k plus 1. So it's very good in alpha. Of course, the gate complexity of this increases because you have to be able to implement this nested commutator. So this is something that maybe for future work, how do you make that actually better? So just to show a bit of numerical results, so here we first took a model where you can actually go to, it's fast forwardable, so you can go to many very large sizes. So here we take, in the same spirit as the first graph, we took a time that scales with the system size, and just look at different algorithms. Like in the left, there is essentially a parameter plot of like the value of alpha that we are taking and the evolution time. So the value of alpha is on the vertical axis, and the evolution time is on the horizontal axis. And essentially, we see that in this case, we dominate the landscape with our algorithm. So the different colors are the different algorithms. The different shadings are like the error that they achieve, and there's these like contour lines that hopefully you can see. And on the right, we also look at, you fix the gate depth, and such that you can put one realization of the costlier algorithm, and then you compare across. So you fix your gate depth, and then you generate the algorithm many times. And we see essentially, something I just want to point out, that this optimized Thrift 8, which is like an 8-product formula that using results from the literature, we can actually use our results on top of that to get a scaling that actually goes lower than, with a scaling that is smaller than like linear in time, which is really interesting. This model is fast forwardable, so this is not impossible. But what's really interesting is that the algorithm is somehow able to find that this model particularly can be simulated faster than time, the total evolution time. Just to there's these two. Okay, I think I will skip this for the. But essentially, here we use 2 formulas that are in the literature, which are like improved, just normal Toder formulas. You know that if you want to go to an order k Toder formula, you have to use essentially an exponential number of single exponentials, and that exponential scales with the order. So that's some price that you have to pay. But you can reduce the constant in that exponential. So this Morales and all paper, they actually look for a numerical way of getting this exponential of 8 order with just like, I think like 17 exponentials, which is very good. Just another numerical example. This is on the transverse field Ising model in 2 dimensions. So this is not fast forwardable, but we can just do simulation time up. So here we are in the first plot is the same as before, but the second one, instead of simulating with for different times, we just increase the simulation time for a fixed 3x3 lattice, because we cannot go larger, because the model is not fast forwardable. But we see kind of similar features. This is again the third model, which is the Heisenberg with random field, which again we see that our methods outperform all the previous ones. How much time do I have? Okay. So yes, to conclude, the nice thing about this work is that we have like 2 kind of things that go hand in hand. We can provide like provable guarantees, like we can prove that this thing is better in the scaling limit when you take alpha to be very small compared to standard product formulas, and the costs are comparable. And here more a general idea, like in the vein that has been discussed before. Like when you want to solve a problem, you know something about your problem. You know your Hamiltonian, you know your state. So use that to your advantage to create better algorithms. And more generally, like we have seen all this mounting evidence numerically that there are like these nice error bounds that we can kind of prove, but essentially those are sometimes not very tight. So you can usually do better, improve the constants, which is good if you actually want to implement these algorithms. So with that, just I want to thank everyone.
Okay, any questions? So you showed numerical simulation results. Have you also studied this on devices, or?
No, we are in the process of doing that, but no results yet.
Great. Okay, let's. Yeah, go ahead, T.
If we use different error metrics, say taking into account the initial condition like low subspace and so on, error bounds can be improved. Do you expect your product formula can also improve around with respect to that?
Yes, I do, because here we study the worst case scenario, which is like operator norm. So and we improve there. So there's no particular reason to expect that it won't be actually improving in particular more constrained scenarios. Yes. Thanks.
Okay. Yeah. Any last questions? So let's thank the speaker again.